We are live, sir.
So welcome again to the GATE Academy. Okay, we are running a series on the new things that have been added into GATE 2021 examination. And in this lecture series, we are covering about our steam turbine and gas turbine. So this is our third lecture in this series. This is our third lecture in the series of steam turbine and gas turbine. Okay, this is the third lecture. So if you haven't seen the previous two lectures, please go and subscribe the GATE Academy channel. Okay, and see those videos. Okay, so firstly, let me tell you something about myself. Okay, so who am I? So my name is Umashankar Tripathi. I'll take very less time here now because this is the third video in this lecture series. So my name is Umashankar Tripathi. I am currently a PhD scholar at IIT Roorkee. Usually people call us like research scholar. Okay, so before PhD I have completed my MTech from IIT Roorkee itself. As far as my GATE rank was concerned, my GATE marks in 2014 was 65.66 and 2015 was 77.02. On the basis of this, I took admission in MTech program of Indian Institute of Technology Roorkee. Okay, Indian Institute of Technology Roorkee. Okay, so right now I am a PhD scholar, and as far as my teaching experience is concerned in the GATE domain, I have been teaching into various centers of the GATE Academy across India from past 8 years, from past 8+ years. Okay, so in this lecture series, as I told in the previous lectures also, our motive is to cover what has been added newly into GATE 2021 syllabus. Okay, so let's see what we have covered till now. So yesterday's class, in previous two lectures, you can find that on the GATE Academy English channel. So I request you to please subscribe that. So we have completed this. Now we are going to see flow through nozzles part 2. Okay. So in this lecture, in this 2-hour session, we will try to complete the flow through nozzles in all respect. We shall try to complete the flow through nozzle in all respect. Okay. So let us begin. Meanwhile, good morning, Prince Raj. Meanwhile, you can subscribe the channel. You can certainly subscribe the channel. So what we have learned yesterday, now you can see on the screen. You can see on the screen what we have learned yesterday. Okay. So we have seen. Good morning, Vrinder. We have seen the velocity of sound. We have seen the expression for velocity of sound. Yes or no? So let me open another one. Okay. So what we have seen yesterday in the previous lecture, we have seen the velocity of sound. Okay. We have seen why we require to use velocity of sound in the analysis of the nozzle, flow through nozzles in the steam turbine, flow through the nozzle in the steam turbine. Okay, flow through the nozzle in a steam turbine, and in what conditions the velocity, the compressible flow comes into picture. In what condition the compressible flow comes into the picture. So yesterday we have seen the formula of velocity of sound in isentropic condition. So we call it C. We call it as C, and we have derived this formula under root of gamma into R into T. Then we have seen what? We have seen the Mach number. We have seen the Mach number, right? We have seen the Mach number. Just a moment. Some technical error is there, so no, it is okay. Okay. So we have seen the velocity of sound. That is equal to C. That is equal to under root gamma into R into T. And as I told, we can strictly use this formula in isentropic condition. Then we have seen the Mach number. We have derived the Mach number as equal to velocity of test fluid upon velocity of sound. And then in the last lecture, we have seen the stagnation properties as well, and we have developed some expression for stagnation properties. So this much we have seen. This much we have seen in the previous lecture. And in the first lecture, we have seen the introduction to steam turbine, how what we are going to learn in this new edition, how it is different from the old existing gate syllabus and what to write, how to write. And in a steam turbine, how is the broad, like I told in the first lecture, that a steam turbine is nothing but the combination of nozzle and moving blade. So in that lead, we are analyzing here the nozzles. So this is our second lecture for nozzles, and for steam turbine, this is our third lecture. So if you haven't seen the previous lectures, please subscribe the Gate Academy English channel and firstly see that, then you will be able to understand this lecture even better. Okay. So today, what was our target? We are analyzing the flow through nozzles. So for that purpose, we require to design the nozzle. And we have seen yesterday that its Mach number is less than 1. We have seen the Mach number is less than 1. It is called subsonic. Mach number is 1, then it is called sonic flow. And if Mach number is greater than 1, we will call it as supersonic flow. So let's say we have to do what? Let's say we have to analyze the compressible flow. We have to analyze what? Compressible flow. And as I told in previous lectures also, that this part is common in two subjects. Okay, compressible flow, is added in fluid mechanics, and a steam gas turbine is added in the part of thermodynamics. So compressible flow in passage of varying cross section. Okay, so let us do how compressible flow can be managed. How compressible flow can be managed in passage of varying cross section. How compressible flow can be managed in passage of varying cross section. Compressible flow can be managed in passage of varying cross section. Okay, so for that, let us see something first. That what we already know. So if the flow is incompressible, now listen to me very, very carefully. If the flow is incompressible, and flow is taking place from 1 to 2. Flow is taking place for 1 to 2. So let us say that it is an incompressible flow. So in the previous syllabus, we do have the understanding of it. What we say, how we say it. We use our continuity equation. We will say this like this: that A1 V1 is equal to A2 V2. I think this equation most of you are aware of. Yes or no? This equation most of you are aware of. So A1 V1 is equal to A2 V2. A1 V1 is equal to A2 V2, or we can write AV is equal to C. So those are who are in the live, so they can reply me in the chat as well. I will answer and I will see how you are responding or not. So AV is equal to C, we know. So how we can do it? So if I do something like this, AdV plus VdA is equal to 0. I don't think there will be any problem. So we can write like this as well: dV by V is equal to minus dA by A. dV by V is equal to minus dA by A. Right? So if I say in this, what is a nozzle? In previous lecture, I have defined what is the nozzle. So nozzle is something in which the velocity increases, means you have to design a passage. Now, listen to me very, very carefully. We have to design a passage in which the design should be like that, that during the flow, the velocity of fluid increases, and during the flow, the pressure of fluid decreases. Then only you can name it nozzle. Otherwise, you can't name it nozzle. It is something else. So now, if this section, if I am seeing, so we call it in English like converging section. So let's say a flow of incompressible fluid is taking place in a converging section, in a converging section. So in a converging section, what is happening? Area decrease. Okay, in a converging section, what is happening? Area decreases. So when area decreases, we can say that the change of area, this dA, this mathematical dA is also decreasing. This mathematical dA is also decreasing. So dA decreasing means dA is negative. Very simple. dA is negative. It is decreasing means dA is negative. So dV will come out to be positive. If you place something negative here, so negative will be positive. dV will be positive. So we can say that velocity is increasing. So I think you already know all this. Okay. This is a very usual saying that if area is decreasing, our pressure, if area is decreasing, our pressure decreases, and our velocity increases. So how the area is related with the velocity, we can have the idea from this equation. Now, is there any doubt in that? Do we say like this or not? That's in incompressible fluid. If incompressible fluid, what we have learned, that whenever the area decreases, the velocity increases, and with the increase of velocity, the pressure certainly decreases. With the increase of velocity, the pressure here decreases. Right? Is it right? So how I am doing this? I am doing this by using continuity equation. So let's say now I want to do it for compressible flow. Let's say the flow is compressible. It's a very interesting topic, very simple, and a very good topic from which questions can be certainly asked in GATE examination. Okay, these kind of conceptual things are usually asked in the GATE examination. Okay, so in the compressible flow, all of us know that we can write the continuity equation like this. Is that so or not? Is it true or not? We can write compressible flow equation, continuity equation of compressible flow like this: rho A V is equal to C. Okay. Simply, if density is not constant, the mass flow rate is constant, we can write like this. So I think all of you certainly know this, because this is already was in previous syllabus. As I am telling in you all the lectures, that we are here interested in covering what is new. So from here, if I can write like this, sir, rho V dA plus rho A dV plus AV0 is equal to 0. I don't think there will be a problem. So if I divide this equation with rho AV, I can write like this: dA by A plus dV by V plus d rho by rho. Yes or no? So dA by A plus dV by V plus d rho by rho is the differential form, we can say, of the continuity equation valid for compressible flow. Is this stuff? Very easily we have done it. Yes or no? Now, what is our interest? Here? Our interest is to see, because we are designing the nozzle, our interest is to see that what will happen if I decrease the area, and what will happen if I increase the area. So can I write this like this? Let's say this is equation number 1. Let's say it is equation number 1: minus dV by V minus 0 by rho. Okay, dA by A is equal to minus dV by V minus 0 by rho. Okay, so we can certainly write like this. Yes or no? So what is troubling us here? That's we can say, sir, this d rho by rho is somewhat troubling us. Why it is troubling us? Because it is restricting us to see the relation between the area and the velocity. It is restricting us to see the relation between area and the velocity. So what we must try to eliminate here? We must try to eliminate d rho by rho here. We must try to eliminate d rho by rho here. Is that right? Is that right? So how we can do it? How we can do it? So there is another equation that we see. There is another equation that we see in fluid mechanics or in thermodynamics known as steady flow energy equation or Bernoulli equation. Steady flow energy equation or Bernoulli equation. So if I write like this, dp by rho plus vdv, dp by rho plus vdv plus g dz is equal to 0, you may call it Euler equation. Okay, the same thing. See, as I told in the previous class, same thing. If you see any thermodynamics book like Pikenag and anything, any power plant book which is following the thermodynamic approach, you will find that these expressions which I am going to derive from Euler equation has been derived with steady flow energy equation. It makes no difference. It makes no difference. Okay, so what I am trying to do is that you understand the things which is common in both the subjects. You don't have to understand, you don't have to learn one thing for fluid mechanics, one thing for thermodynamics. So we are studying in a way that we are developing the content which is useful for both the subjects, not only for thermodynamics, not only for fluid mechanics. Okay, is that right? So we have seen this Euler equation. So let's say our datum is constant. We are not changing as you can see in this incompressible flow thing that we are not changing the datum. So datum is constant. So we just extract it out. Okay. So what I require here, I require d rho by rho. So if I write like this, dp by d rho, now see what I am doing. So dp by rho is here. If I multiply our d rho here and divide our d rho here, will it make any difference? Will it make any difference? Tell me that. Will it make any difference? Tell me. Will it make any difference? Tell me. No, it is not going to make any difference, right? dp by rho into d rho by rho, I wrote like this. So from here, I can write d rho by rho into dp by d rho So dp by d rho is nothing but our velocity of sound. We have seen in previous lecture. That is why I am saying, if you are seeing this lecture directly, go and subscribe the Gate Academy channel and the Gate Academy English channel and find the previous videos of it. This is the third lecture. So in the previous lecture, we have derived this relation. That the velocity of sound is under root of dp by d rho. The velocity of sound is under root of dp by d rho. So dp by d rho I can replace with c square, and it will be equal to minus vdv. It will be equal to minus vdv. So if I make some more changes, let me multiply a velocity in the numerator and a velocity in the denominator. So it will be like v squared dv by v, So we can write like this. D rho by rho is equal to minus m square dv upon v. Is this right or not? What we have done now, we are using the value of velocity of sound as we are using the relation we have developed in the previous lecture about Mach number. So Mach number is nothing but v upon c. So here we have developed a relation between density and velocity. Here what we have developed a relation between density and velocity. So now tell me if we have to see that how the velocity is changing with respect to density or vice versa, we require to incorporate the Mach number as well, because then only you can tell. Yes or no? So this relation can be used for telling the changes happens in a velocity with respect to density or vice versa. So let's say this is our equation number 2. Let's say this is our equation number 2, and let's say this is our equation number 1. We already put it as equation number 1. So let's place the value of d rho by rho. Let's place the value of d rho by rho in the equation number 1. So how we can do it? dA by A is equal to minus dV by V, and we are placing the value of d rho by rho here. Just simply we are placing the value of d rho by rho, d rho by rho. In this kind of topics, you all must sit with your copy and pen. Otherwise, at the end, you won't be able to understand anything, because so many relationships are coming up. So many relationships are coming up. And as I recommended you earlier also, you do not require to memorize all these formulas. These formulas are very difficult to memorize. So do it with what you know. You know this, you know this, you already knew this. So I am only doing whatever I am doing from these two relations only. Okay. Just 2-3 lines you have to write, and you will develop the formula. So my suggestion is to not to memorize all this, not to memorize all this. Okay. So this is coming out to be m square minus 1. M square minus 1. So this is a very important formula. This is a very important thing that we require. This is a very important thing that we require to focus here. We require to focus here. So let me mark it as very important. Okay, why it is very important? Because this is giving us the change of velocity with respect to James Muller. The notes will be uploaded on the Gate Academy English channel. You can find it here. For that, you have to subscribe the channel. You have to subscribe the channel. We will upload the notes in the channel itself. Okay. So very important, dA by A is equal to dV by V, m square minus 1. So this is very, very important relation. This is very, very important relation. And what we are going to do is, what we are going to get from it, we are getting here the relationship between area and velocity. So from this equation, we can comment that if the area is changing, what will be the changes of velocity, provided we have the value of Mach number. Provided we have the value of Mach number. Now observe. In the case of compressible flow, this is the cloud over the incompressible flow. In case of incompressible flow, you can observe here that we can comment the changes in velocity with respect to the area without considering or without using the Mach number, because here Mach number is not required. In this relation, Mach number is not required. So in incompressible flow, you need not to worry about the Mach number. You need not to worry about anything if area is decreasing. If area is decreasing, velocity will certainly increase. And pressure will certainly decrease. So if you have to design a nozzle, very important statement I am writing here. If you want to, what we are doing here, we are designing the nozzle. If you want to design a nozzle. Okay, and nozzle is what? In which velocity increases, pressure decreases. So if you want to design a nozzle, the area must be what kind of passage you must make? You must make the passage in which the area is converging. If not, it will act as a diffuser. So the design of nozzle is completed for incompressible flow. That we already knew. Yes or no? That we already knew. Okay. So if you want to design a nozzle for incompressible flow, our design is over. But if you see this relation now on your screen, you just can't do in the same way as you have done. You can't do in the same way as you have done in case of what? In case of incompressible flow, because here we can write it in very big letters. Mach number is involved. Now here Mach number is involved. So now you can also understand the significance of Mach number in the design of nozzle, So let us also derive the relation of pressure in it. Let us also derive the relation of pressure from it, so that we are able to see the changes of pressure. We are able to see the changes of pressure with respect to area, because nozzle as we have defined is something in which velocity increases and pressure decreases. So let us also develop the relation between the pressure and velocity. So dp by rho, from Euler equation, dp by rho is equal to minus v dv, is equal to minus v dv, is equal to minus v dv. Okay, this is from Euler equation. So we can write it like this: v square dv by v, v square dv by v. So from here itself, the things are very much clear. We do not need to go further, but we will, because these relations can be asked in 1 marks or 2 marks in gate examination. Some direct question may arise. So from here itself, it is very, very clear. That even in a compressible flow, this v square entity is positive. So dv, if decreasing, dp will be increasing. Yes or no? Or vice versa, if dv is increasing, means the change of, we should write like this, that if dv is positive, means what? That the velocity is increasing. So from here, dp is coming out to be negative. So pressure decreases. So pressure is what going to do? Pressure is going to get decreased. Okay, decrease. So otherwise, what can happen? dv can be negative. dv negative means velocity decreases. So if velocity decreases, so minus will become plus, and dp will be positive. So pressure increases. So we can conclude here that either the flow is incompressible or the flow is compressible. With velocity, the pressure observes inverse relationship. Means if the velocity is increasing, either it is incompressible or compressible flow, the pressure will decrease, and vice versa. Is that clear or not? So in any kind of flow, either compressible, incompressible flow, the velocity when increases, the pressure certainly decreases. Although we are going to see it with the formula as well. So in this thing, what you can do, you can place dp by d rho is like dv by v. We have already developed from here. So let me place the value. Let us spare minus v square here. So it is like dv by v. We can write like dA by a upon m square minus 1 upon m square minus 1. Yes or no? I have just replaced the value of dv by v from equation number 3 into this equation. Nothing very typical. So dp by rho, we may write like this: v square. If I send this minus inside this bracket, so it will be like 1 minus m square dA by a. So this can be used as a relation to find the changes of pressure with respect to area if I have some value of density, and velocity. But the relation between velocity and density, that what will happen with velocity and pressure, we can already observe. We can observe from this relation. We can certainly observe from this relation. True. So now, till now, what we have done, we have developed the relation between velocity and density. So if a question arises to compare between velocity and density, we certainly can answer. We have derived a relation between velocity and area, change of velocity and change of area. So we can certainly comment upon, if the area is changing like this, velocity will be changing like that. And if we have to change the velocity like this, the area must change like this. We can comment all this. Yes or no? Similarly, with pressure, we have related now with pressure with velocity. And now in this last relation, we have related the pressure with area. So these all relations are just complementary to each other. They are not independent to each other. If you can develop one relation, from one relation, another relation will arrive, and from another relation, another relationship will arrive. So it is very hard. It is very hard, according to me, to memorize all these formulas. So what we can do here, we can go for the basics. We can go for the basics, the things we already know. So I think my suggestion, develop everything from this equation that we call as continuity equation, that we call as continuity equation. I think everyone is aware of it. So continuity equation and this equation, this Euler equation. Okay. So these two equations we are very much aware of. So we can use these equations to get all these formulas. Okay. So now I have to design my nozzle. I have to design my nozzle. So if I have to design my nozzle, let me copy this relationship and see what is going to happen. See what is going to happen. So we have this relation copied. And we are going to design nozzle here. Okay, so we have already done so. Did so for incompressible flow. So now if Mach number is less than 1, we can call the flow as subsonic. Okay. Now what we want to develop a nozzle in which subsonic flow is happening. Now take care of my wording. Sir, I am using this word nozzle again and again. So whenever I say this term nozzle, it means we have to increase the velocity and decrease the pressure. So we are designing here. So how we design the passage? How should be the passage? So that the velocity increases? So what we want? We are developing a nozzle. Now see, we are developing a nozzle. So in nozzle, what must be there? Velocity must be increased. So velocity increase, to increase the velocity, and this Mach number is less than 1 for subsonic case. So this Mach number, when less than 1, this Mach number is less than 1. So in this relation we can certainly say, now see, in this relation, if Mach number is minus 1, in this relation, if Mach number is minus 1, observe here, please. Observe all this. So if in this relation Mach number is minus 1, this entity is certainly going to be a negative value. Virender, we have to see, like you are asking, sir, in this formula, we have to take the density as initial or not. Sir, the changes of density we already have observed with respect to velocity. Okay, so we can take rho and v as constants here, and we can relate between dp dA by A. Just we are trying to, this relation is, what is the significance of this relation? This relation is significance is that we have to relate the pressure with respect to area. So we are considering rho and v as constants here. Okay, as constants in the sense that their sign is not changing. Their sign is not making any influence. Their decrease or increased tendency is not giving any influence between the relation of pressure and area. And as I have explained here also, that dp by d rho, see here, dp by d rho is equal to minus v square dv by v. So we have already established the relation between pressure and velocity, and we have concluded that whenever the velocity is increasing, the pressure must decrease, and vice versa. So now coming back to this discussion. So if m is less than 1, so if Mach number is less than 1, and I want everyone who is live to respond on it. So if the Mach number is less than 1, this quantity, this in which I have made a circle kind of thing, so this is negative. In subsonic flow, this entity is negative. Yes or no? Yes or no? So we can say for subsonic flow, dA by A is something of negative, something of negative. There must be some value here. There must be some value here. We are not interested in that. We are not interested in that. dV by V. dV by V. Okay. Okay. How this comes? How this comes? You are able to understand or not? I think everybody who is seeing this video or live in this class must be able to understand this. So this entire entity is negative. So we have this negative value here. So now we have to increase the velocity. We are making the nozzle now. We are making the nozzle. So dV must be positive. Yes or no? For nozzle, for nozzle, dV must be positive. So for nozzle, if dV must be positive, dA must be what? If dV is positive, means velocity is to increase. Velocity is to increase. dA is negative. dA should be negative. dA should be negative. So dA is negative means area should be decreasing. Area should be decreasing. So these are my observations, or these are our observations for the design of nozzle. For design of nozzle in subsonic condition, that is when Mach number is less than 1. These are our observations for designing of nozzle when Mach number is less than 1. One Mach number is what? Mach number is less than 1. Okay. So we must design like that. We must design like that. We must design like that. The area is decreasing along with the flow. The area is decreasing along with the flow. So from here to here, say, let's say from 1 to 2, from 1 to 2, from 1 to 2. If our subsonic compressible fluid flows, its velocity will certainly increase and pressure will certainly decrease. As we have established, with velocity, pressure always decreases. Pressure always decreases. Or you can check by this relation also. You can check by this relations also. So for subsonic flow, you can certainly say that this one is positive, this one is positive. So with decrease in area, with this decrease in area, pressure is also decreasing because this is positive. So if dA is negative, dP is also negative. dA is negative, dP is also negative. So we can certainly say by any view you can see, by any view, by any relation you can see, the relationship will come out to be the same. But we are trying to make things simpler for you here. Okay, simpler for you here. So can I say our nozzle is successfully designed for subsonic flow? So what is our final observation? So for subsonic conditions, for subsonic conditions, for subsonic conditions, for subsonic conditions, the nozzle, or for subsonic condition, the passage, let me say the passage should be converging. Passage should be converging to act, converging to act as a nozzle. Is there any doubt till this point? Is there any doubt till this point? Is there any doubt till this point? Now tell me. Tell me. Tell me, is there any doubt in this point? Understood? Is it easy or not? Are we making it difficult? Okay, now listen to me. Now listen to me. Yesterday's first lecture, we have established something. What we have established, sir? What we have established, sir, that in Rankine cycle we see, that after the exit of boiler, this is the Rankine cycle. No? Let me now do these things. Let me do these things with respect to the Rankine cycle now. We already know about the Rankine cycle, so I am fitting whatever we have learned till now to the to the Rankine cycle, to the steam turbine thing, so that you come to know that why we are studying all this. So now in Rankine cycle, what is there? There is a pump. We have discussed all this in a very brief manner. Why brief manner? Because we are here covering the new syllabus, not the old one. So we at Gate Academy do not do things like that, that we write something and we teach something else. Okay, so when we say we are teaching the new syllabus, we are teaching the new syllabus only. So this is boiler. This is boiler. Okay. This is a steam turbine. This is our steam turbine. So this is till now from the existing knowledge which was already in the syllabus, we knew all this. So this is pump. From pump it is going in 2, coming out boiler in 3, and coming out from the steam turbine at 4. So yesterday's class, in the previous lecture, what we have seen, in the first lecture of the series, we have seen, sir, what we were seeing in the previous syllabus at just the steam turbine, from where our network output was coming out to be H3 minus H4. Now we have seen that, sir, this is the combination of nozzle plus moving blade. Nozzle plus moving blade. Now tell me one thing. Now answer me. If the 3 is in subsonic condition, if the state 3 is in subsonic condition, if the state 3 is in subsonic condition, so can we say that our fluid, our superheated steam is entering into the nozzle in subsonic condition, Now, if I may ask you that if the condition 3 is subsonic, how should be the design of your nozzle? How should be the design of your nozzle? So if entry and exit both, if entry and exit both are subsonic, both are subsonic, from this 3 point, what we say, the entry to the steam turbine till now. So now we say that this 3 point will go into the nozzle, and we should make the nozzle like this. We should make the nozzle like this. And it is coming out from the nozzle at the point 3 dash. So if both 3 and 3 dash are subsonic, our nozzle should be converging. And there with high velocity it will enter the moving blade, and there it will convert its high velocity energy into the impulse and will make the wheel rotating. So for subsonic, for entry subsonic and exit subsonic, for subsonic entry and subsonic exit condition into the nozzle, we have successfully designed the nozzle, and we have concluded that in subsonic condition our nozzle should be converging. So is there any doubt till this point? Yes or no? Yes or no? So we can also say this observation is exactly same what we have observed in the case of incompressible flow. Yes or no? You can reply back to me in the chat. Is that clear till this point? Everybody can reply me who are present in this live session. Saurav, Ashwarya, sorry. Okay. So I hope you are understanding all these things. So let us see further. So if m is greater than 1, so if m is greater than 1, we have seen it in the previous lectures that, sir, if m is greater than 1, we can say that our flow is supersonic flow. Our flow is what? Our flow is supersonic flow. Okay. So if the flow is supersonic, what relation we are having here? Again, I am copy pasting the same relation. See everything we can do, and all this we have derived from nothing but nothing but our continuity equation and our Euler equation. So nothing new in all this. Nothing new is all in all this. Okay, people these days are claiming this to be very difficult days. Nothing difficult in all this. Okay, so now if m is greater than 1, if m is greater than 1, so this m is greater than 1, this m is greater than 1. So if m is greater than 1, this will be certainly positive. Yes or no? Common sense. Okay. If m is greater than 1, this clouded entity will be in positive. Will be in positive. So we are here to design the nozzle. So as I said before as well, if we name something as nozzle, in it the velocity must increase. In this, velocity must increase. Means what? If we want to increase the velocity, dv should be positive. dv should be positive. If we want to increase the velocity, dv should be positive. dv should be positive. So if in order to make dv positive, dA should also be positive. dA should also be positive. And dA positive signifies that, dA positive being positive signifies that our area must be increasing too. Our area must be increasing too. Yes or no? Yes or no? So these are our observations for nozzle. These are our observations for nozzle in supersonic condition. In supersonic condition. Yes or no? These are our observations in supersonic conditions. Yes or no? Yes or no? Yes or no? Okay. So if we are having supersonic flow, if we are having supersonic flow, so can we say in order to increase the velocity, in order to increase the velocity from entry to exit, if in order to increase the velocity from entry to exit, in order to increase the velocity from entry to exit, we must make our nozzle like this. We should make our nozzle like this. That means in English we call it diverging. Diverging. So in supersonic condition, in order to increase the velocity, you have to increase the area. And if the velocity is increasing, the pressure will be decreasing again. Pressure will be decreasing again. So these is, so how must you design the nozzle in supersonic condition? So it must be diverging. It must be diverging. So for a moment, just for a moment, imagine that we have converging passage. Just for a moment, now see, just for a moment here, imagine that our passage is like this. Our passage is like this, because generally what is in our mind till now, that if something is to be work as nozzle, is the area must be converging. Its area must be converging. So this is what people generally understand, that nozzle means what? Area is decreasing. So it is not like that. So now see, if by any chance we have a converging passage and supersonic flow is happening here, supersonic condition is here, supersonic condition is here. So what will happen to the velocity between, let's say, 0.1 and 0.2? What will happen to the velocity? So we are seen from this equation, we have seen that in this, area is decreasing. So area is decreasing, so dA is negative. Area is decreasing, so dA is negative. dA is negative, so dA is negative, then velocity will also be negative because this entity is positive. So velocity will also be decreasing and pressure will be increasing. Pressure will be increasing. So if by any chance supersonic flow comes to happen in our converging section, the velocity will no more. Velocity will no more increase. Velocity will no more increase. Otherwise, on the other hand, it will decrease. On the other hand, it will decrease. And as we have learned in our first lecture, what is required in an impulse turbine? That nozzle increases the velocity. What is required in an impulse turbine? That the nozzle increases the velocity. The nozzle increases the velocity, and that velocity happens to create impulse or change of momentum on the blades. Due to which we get our torque and we get our electricity. So think for a moment. Just think that some engineer who do not know this, And in steam turbine, the flow is supersonic, and he has made a converging section. He has made a converging section. So will our moving blade will rotate, and do we have the electricity then? Do we have the electricity then? So yes, we do not have the electricity then. So the design of nozzle, that's why it's very crucial, so that our steam turbine is running fine. Is that clear? If it is all clear, you can tell me in the chat. You can tell me in the chat. Okay? Okay. This is not clear, Anirban Majumdar? Is it clear or not? Clear. Okay. 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 So if you are liking all these videos, please subscribe the Gate Academy. You are getting some good content. If you think, please like the Gate Academy, subscribe the video, subscribe the Gate Academy, like the video, share it to your friends. So now we have seen now what conclusions we have made till now. What conclusion we have made till now. So I am writing some conclusions here, because so I think conclusions. Previously I was making a spelling mistake. So conclusions. So what are the conclusions we have made till now? So if the flow is incompressible, if the flow is incompressible, now listen to me. If the flow is Anirban, what you are saying, I am unable to understand. If the flow is incompressible, if the flow is incompressible, if the flow is incompressible, the nozzle must be converging. The nozzle must be converging. If the flow is incompressible, the nozzle must be converging. Okay, if the flow is incompressible, the nozzle must be converging. Okay, if the flow, now listen, if the flow is subsonic, if the flow subsonic, or we must write like this: if the entry and exit, if the entry and exit condition is subsonic, if the entry and exit condition is subsonic, the nozzle should be diverging. The nozzle should be diverging. Okay. Okay. Similarly, if the entry and exit both, if the entry and exit condition are supersonic, the nozzle should be oh sorry, I have made a mistake here. It is converging. It is converging. If the entry and exit condition is subsonic, the nozzle should be converging. Okay, because it is a subsonic thing. So we have seen it must be converging. And if the entry and exit condition are subsonic, the nozzle should be diverging. The nozzle should be diverging. But you can here understand something, that to make the entry condition right from the start, right from the entry, is very difficult, because see in our power plant what is happening, before entering to the nozzle, the steams come out from the steam came out from the boiler. The steam came out from the boiler. Okay. So here in pump, in boiler, in condenser, the velocity is not that much increasing that it will go to a supersonic state, because supersonic state, you know, it must be greater than the velocity of sound. So this much velocity we do not attain after the boiler in general. Okay, so normally the nozzles are from the beginning they are not diverging, because it is a very rare condition where the entry to the nozzle is in supersonic condition. But as we have developed, if it is in a supersonic condition, that nozzle must be diverging, or we can say in supersonic flow, in order to increase the velocity, the area must be increasing or the passage must be diverging. So am I clear till this point? All these things are clear till this point? Yes or no? Yes or no? You can reply back in the chat. Please tell me if everything is clear to you. Tell me. Now, very important discussion is going to happen here. Very important discussion is going to happen here. Virender, please tell me the doubt. So very important. Yeah, ask the doubt, beta, no problem. Sonic condition I am dealing with. This is the very important condition. At the sonic condition, when m is equal to 1, that is v is equal to c, we call it as sonic condition. Virender, if the entry is subsonic and exit is supersonic, we are going to deal with that. Don't worry. Just wait. We are going to deal with that. So if the Mach number is 1, we call it as sonic flow. Madhusmita, we are going to deal with that only. You are asking what will be the design of nozzle in sonic conditions. So here this is the third case. We have seen two cases till now. That when the m is less than 1 means we are now knowing to design the nozzle in subsonic condition. Okay. Here we are knowing to design the nozzle in supersonic condition, and now what we are going to do, we are going to design the nozzle for sonic condition, or we are going to see what is happening in the sonic condition. We are going to see what is happening in case of sonic condition. Okay, so not only we are going to see the subsonic entry to subsonic exit, we are also going to see subsonic entry to the sonic exit. We are also going to see the subsonic entry to supersonic exit. Don't worry about it. Now see, now listen. Now if m is equal to 1, let me again copy the same equation I have copied once. So now see to me. Now see here. Let us see here. Now see. We have this relation. Now tell me. Listen each and every word very, very carefully. Otherwise, you will get confused here. Okay. Now see. If m is equal to 1, as in this case, m is equal to 1, can we say dA is equal to 0? If m is equal to 1, m is equal to 1, simple mathematics we apply, we can say if m is equal to 1, dA is equal to 0. Yes or no? Okay. So in English, can we write like this? That if the flow is sonic, the area is constant, or the area must be constant. Can we say like this or not? Now tell me yes or no. If the flow is sonic, the area must be constant. Yes, Virender, we are doing that. Just follow the lead, you will come to know. Just try to answer the question I am asking. You are saying, sir, we are designing nozzle as per what value will be the outlet of Mach number? Na? Yes. Then only we come to know na, that in the exit, the flow is sonic or subsonic or supersonic. Okay, so Mach number is certainly very, very important here. Okay, so M is equal to 1, dA is equal to 0. So we can conclude if the flow is sonic, the area must be constant. The area must be constant. Now tell me, is it possible? Is it possible from the mathematics what you are seeing right now, right here, right now, is if the flow is subsonic, the area is changing. So either any one thing has to be changed. What I'm trying to say is, if Mach number is 1, if Mach number is 1, the area must be constant. Or if area is not constant, if area is not constant, means dA is not equal to 0, means dA is equal to not equal to 0. If listen to me very, very carefully, if area is not constant, that means dA is not equal to 0. So M can't be 1. Yes or no? Yes or no? If area is not constant, that means dA is not equal to 0. M can't be 1. Yes or no? M can't be 1. So these two statements are just complementing each other. If you try to understand it, if any one of it is not followed, the second will not be followed. Got my point or not? If M is 1, now listen again. If M is 1, the area must be constant, and if area is constant, the M should be 1. The M should be 1. If you want to have some change in velocity. Yes or no? Yes or no? Got it or not? Now leave the velocity thing. Just see it. If the M is 1, the dA is equal to 0 means area is not changing, and we have made a passage of uniform cross section. We have made a passage of uniform cross section. So if the flow is sonic, the passage must be uniform cross section. The passage must be of uniform cross section, and vice versa. Vice versa means if the passage is of uniform cross section, the compressible flow should be sonic. How I am commenting on this? If cross section is uniform, yes, Madhu Smita, it will be converging, diverging type. We are coming to that only. Now please see. Now please listen to me very, very carefully. Otherwise, you won't be able to understand this. So if cross section is constant, if cross sectional area is constant in a passage, so what will be there? So purely using mathematics, dA by A, we are saying like dV into m square minus 1, dV by V into m square minus 1. This is our relation. So cross section is constant means what? That dA is equal to 0. So for dV not equal to 0, because if dV is equal to 0, the flow won't happen, because dV is equal to 0 means the pressure is not changing. And we all are aware of this fact that in a passage, if pressure is not changing, flow won't happen. Yes or no? So if dV is not equal to 0, then what should be equal to 0? M square minus 1 should be equal to 0 to satisfy this mathematics. Yes or no? Satisfy this mathematics. So M should be equal to 1. Yes or no? M should be equal to 1. Yes or no? So for sonic flow, when the velocity is equal to the velocity of sound, when the velocity becomes equal to the velocity of sound, the area should be constant. Otherwise the flow cannot be sonic. Okay, flow cannot be sonic. Yes or no? Madhusmita, are you able to understand this point or not? Madhusmita Roy. Yes or no? Are you able to understand this point or not? Tell me. Okay, clear. Now see, now everyone should pay their full attention over this discussion. Now let's say, now let's say the entry, let us understand this. Now let us apply all these observations. Now let us apply all these observations. Okay, all these observations. Now, now let's say the entry to the nozzle is subsonic, is subsonic. Okay, the entry to the nozzle is subsonic. Okay, now see, now listen, now see here, now see here. The entry to the nozzle is subsonic means at this point, from this point onward, what kind of cross section we should make, what kind of passage we should make, so that the velocity increases. So we should make we should make the velocity, we should make the cross section as converging, so let's say this point is 1 where it is entered into the nozzle, where, or let's say o. So at the point where the entry of the nozzle happened, entry of the nozzle happened, we named it as v naught. So let's say v naught is equal to zero point 0.4 of velocity of sound, exactly equal to 0 0.4 of velocity of sound. Now flow with me. Now have some flow with the flow of this steam. So now the steam is flowing in this direction, and as the entry to the nozzle is subsonic, while you flow in this direction, the velocity goes on increasing. So at some point, let's say at this point, the velocity become 0.6 of velocity of sound. At this section, I have marked it as this red line. The velocity has become 0.6 of velocity of sound. So can we, now my question is, can we increase the velocity any further? So yes, we can increase. Because the flow is still subsonic. So let's say this point is 1. Okay, so from this one section, can we further increase our velocity? So yes, we can further reduce the area, and while reducing the area, our velocity will increase, because we are in subsonic condition. So let's say we have reduced the area, we have converged it even further, and we have reached this point 2. So now velocity will further increase, and v2 will be greater than v1. And let's say v2 has become 0.9 of velocity of sound. The 0.9 of velocity of sound. So we are still in subsonic condition. Now tell me, if I further decrease the area, velocity will increase or not increase? So velocity will certainly increase. Because still we are in subsonic region. And we have made this conclusion. That in subsonic region, whenever we decrease the area, the velocity will increase. So from 2 point, even if further I decrease the area, even if further I converge this passage, our velocity will go on increasing. Yes or no? Now tell me, is that clear or not? Till this point, it is clear or not? All the observation you are getting from the mathematics or not? Yes or no? Everybody I want response from everyone. Now see, be still and see. Now at this 2 point, our velocity was 0.9 of c, and I have further reduced the area. So from v2, velocity is still increasing. velocity is still increasing. So let's say we have reached the point, where velocity has reached the value of velocity of sound. So let us call this as point 3. So this is where somewhere we have reached the point 3. We are somewhere here where we have reached this point 3, and the sonic conditions have reached. The sonic condition the sonic condition have reached. The sonic condition has reached. Okay, so at this 3 point, the sonic conditions have been reached. Okay, now tell me, at this 3 point, when the sonic condition has reached, the area is minimum. The area is minimum. The area is minimum at 3 of this nozzle. Yes or no? The area is minimum at 3, so we call it as throat. We call it as throat because area is minimum at this point 3. In this point 3, in other words, we can say we can increase the velocity of subsonic flow to the maximum of sonic velocity. We can increase the subsonic velocity to maximum of sonic velocity. Now observe. If I decrease the area any further, will velocity increase? So you can observe in this where I have highlighted. Velocity will not further increase. Velocity will not increase because we have seen once we reach the sonic condition, we require the cross section to be constant, or if we want to further increase the velocity, we should have the diverging section. So in this reason, velocity will not increase. That's why this 3 point is known as choke region. This is the point as choke, or this kind of flow is known as choke flow, because at 3, no more converging will increase the velocity, and if you further converge, the velocity will certainly decrease. Or there may be some shock waves or something of that kind will happen. We will go into that later. But this is a choke flow in which the area is minimum. The subsonic velocity reaches the maximum value till the sonic velocity. Okay, so at the choke flow, what we can say? Now listen to me carefully. At the choke flow, what we can say? Now let me copy this. Again. So now all of you must be able to understand this fact that we cannot increase, we cannot make converging section anywhere further here. So let me call it the choke section, where choke has happened. So I named it as C. So from section 1 to section CC, from section 0 to section CC, what is happening? Till section 0 to section CC, velocity is increasing. From O, the velocity is increasing, and at C, the velocity is equal to the sonic velocity. That means V is equal to C. So we cannot increase the velocity any further. If we are making the nozzle, as a converging nozzle. So in a converging nozzle, how much velocity, what maximum velocity we can get? So in converging cross section, in converging passage, we can increase, we can increase, we can increase velocity up to sonic velocity, that is velocity of sound, up to sonic velocity. Is this observation clear to you or not? And this condition, when you raise the velocity to sonic velocity, is known as condition of choke, because you can't increase the velocity any further. You can't increase the velocity any further. Is that clear or not? Is that clear or not? Is that clear or not? So how must be the design of nozzle? How must be the design of nozzle if the entry condition, if the entry condition, if the entry condition is sonic, sorry, if the entry condition is subsonic and exit condition is sonic. So exit condition is sonic and entry condition is subsonic. So you must design a converging nozzle. You must design the converging nozzle till the throat. So, and at the throat, at the choking point, what we have observed also, at the choking point, at the choking point, at the choking point, or we can say, in other words, we can say choking take place, choking take place in the throat section of nozzle, because in the throat section of nozzle choking take place. If choking is to be taking place, it is not necessary that choking is taking place every time. It is not necessary that choking is taking place every time, because as I said up to, so it is not every time necessary to increase the velocity to sonic velocity. We can have the velocity, exit velocity, equal to 0.9 of sonic velocity as well. So if the exit velocity is equal to 0.9 of sonic velocity, will the choking happen? No, it won't happen. It will only happen when you desire to, increase the velocity in the nozzle to the sonic velocity. Yes or no? Yes or no? Clear or not? So choking takes place in the throat section of nozzle. And what is throat? It is the section of minimum area. 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 It is a section of minimum area in a nozzle. It is a section of minimum area in a nozzle. Okay, in the nozzle. So this choking is very much important. This choking is very much important in understanding the behavior of converging nozzle. So at choking, we call all properties at critical. At choking, we call all properties as critical. So what are the critical properties that happens at that choking point? So if I say what is the pressure at the choking point? What is the pressure at throat? So that pressure we call it as critical pressure. So we are going to derive that. But first let us design the shapes or the cross-sectional variations of the nozzle. So is this clear till this point? The students who are live in this section can reply me. Is this clear in all respect? Crystal clarity is there or not? Tell me, then we'll move further. Now listen to me very, very carefully. Again. So if entry is subsonic, so we have discussed that if entry is subsonic and exit is subsonic, what to do? what to do. So if entry is subsonic and exit is critical, means all the conditions are at its maximum point. Chain, you are asking me critical means all the conditions are at its maximum. No, I didn't said that. I didn't said that. I said critical means at the point where the velocity of the fluid equal to the velocity of sound. So every corresponding property will be the any corresponding property will be the critical properties. Every corresponding properties will be the critical properties. Okay, so if entry is subsonic, and exit is supersonic, now how should we design our nozzle? So if entry is subsonic, now listen to me very very carefully. When entry is subsonic, so in order to increase the velocity, the cross section must decrease. So we are decreasing. Now see, come with me, flow with me. So if the velocity is decreasing, so if velocity we have to increase, as we are talking about the nozzle, velocity we have to increase, we have to converge the section. So as we are going on converging, in this direction the velocity is increasing. Okay, the velocity is increasing, but with this velocity increasing, at some point it will definitely reach the sonic velocity. So let's say our sonic velocity reached on this section, let's say 1 1. Our sonic velocity reached on this section 1 1. So at this point 1 1, v1 is equal to c. At this point 1 1, v1, the velocity of fluid, become equal to the velocity of sound. The velocity of fluid is equal to velocity of sound. So as we have established, if I further converge the section, the velocity will not increase. If I further converge the section, velocity will not increase. But now as we are making a nozzle, we need to increase the velocity. As we are making the nozzle, we need to increase the velocity even further. Then what should be done? We should diverge it. If you want to increase the velocity greater to the c, that is supersonic condition. So we have learned that in supersonic condition, the supersonic condition, the nozzle must diverge. So after the velocity reaches sonic velocity, and if you want to further increase the velocity, you must diverge your cross section. Okay, so from this point 1, you must diverge it, so that the entry, if I call it O, I call it 2. So entry V0 will be less than C. Entry exit at V2 will be greater than C. So that we can say the entry is subsonic. And the exit is supersonic. So in order to change the flow from subsonic to supersonic, if the flow is in the beginning is subsonic and we want to change it to supersonic, how should we make the nozzle? It must converge first, then diverge. And in the middle there must be a throat. This 1 1 represent This 1-1 represent the throat section. This 1-1 represent the throat section at which at which at which the properties at which the properties are critical, and this is also known as critical point or choke point. Okay, throat section at which the properties are critical. So what do we mean by critical? We need to understand them and we need to control them in order to control the situation, in order to control the situation. So are we able till this now, are we able to understand the fact that if we have to make the nozzle, and according to the flow condition, sonic, supersonic or subsonic, which kind of nozzle, which kind of passage we should make so that we get our nozzle, so that we can develop our nozzle. Is that clear or not? Is that clear till this point or not? Is that clear till this point or not? Now tell me. Now tell me. Madhusmita, you were asking the same thing. Is that clear? So what is the conclusion of all this? What is the conclusion to all this? What is the conclusion to all this? The conclusion is what you must understand. What you must understand from all this, that before entering to the moving blade, what shall be the design of the passage of the nozzle? Either it should be converging, either it should be diverging, either it should be converging plus constant cross section, either it should be converging then diverging cross section. So when to use which kind of nozzle, it must be clear till this condition. It must be clear till this point. So as I said, these critical conditions, these critical properties we need to analyze. As I said, this critical properties, this critical condition we need to analyze. So we are going to develop this critical condition. Means we are going to find what is the pressure at critical condition, what is the temperature at critical condition, and so on and so on. So is that clear till this point? If it is clear till this point, you can tell me in the chat box, in the live chatting section. You can tell me. Is it easy or not? Vijay, you are talking about jet engines. Here we are trying to concentrate on a steam turbine. In jet engine, if in some jet engine there is a steam turbine and there is a nozzle and moving blade, the same thing will certainly happen there. Okay, Vijay? So if in jet engine there is a steam turbine which is having some nozzle and the moving blade, this is same for that also. But if we are using the jet engine with some other technology, we cannot comment. Sir, steam, Frozen, you are asking me, sir, steam turbines में sonic boom नहीं होता if the speed is greater than X. That we'll talk about. Okay. Because no, listen to me. In the converging section, what is the maximum velocity we can attain? Now, Frozen, you can answer me this. If in a converging section, what is the maximum velocity we can attain? That is the velocity of sound, yes or no? Yes or no? So when you reach the velocity of sound, in converging section, you cannot increase the speed any further. If the passage continues to be converging. Yes or no? This is what we meant. Yes or no from all this discussion. If once you reach the sonic state, once you reach the sonic velocity, you can further converge. By further converging the cross section, you are not going to get anything. Is that true or not? Tell me. That is true, because we have reached the throat section, we have reached the choked flow, and we have reached we have reached the point where critical conditions are there. Okay, so if you want to further increase the velocity, you can't converge it any further, then you will have to diverge it. Now when you will diverge it, what will happen? What will happen? The velocity goes on increasing again. It will go in supersonic condition. So at some places, if not properly designed, if diverging section is not properly designed, its angle must be controlled. If not properly designed, some shock waves will be generated. What will be generated? Some shock waves will be generated. And once the shock wave is generated, no more change in velocity, no more increase in velocity will take place. Then the rest part of the nozzle will be just behave like as idle thing or a diffuser. Okay. Sir, in converging section, now some Virender, you are asking, sir, now if we in converging section we cannot increase the velocity more than the no, what have you written? Let me just read that. Sir, if we increase converging section more than choke section, velocity will decrease. No. Velocity, if you further converge it, it will be no more a sonic flow. It will become subsonic flow. Okay, it will become subsonic flow. Then you can't call it a nozzle. Nozzle is what? Once the velocity started decreasing, it is no more a nozzle. Once the velocity started to decrease, it is no more a nozzle. Then you can't call it a nozzle. Once you naming it as a nozzle, you must ensure that the velocity is increasing during the flow or with the flow. Yes or no? Yes or no? Got my point? No. Now, our intention is to find this critical condition. Our intention is to find the properties. Properties means what? Like pressure, temperature, velocity, pressure ratio and all. So I will find just one pressure ratio. From that, you can take isentropic relation. You can apply isentropic relation and get anything else. Okay, if we have the pressure ratio, we have the temperature as well, we have the density as well, we have everything. So let's try to find out. Let's try to find out the critical pressure ratio. So for that, let us have a pressure tank. For that, let us have a pressure tank fitted with a converging nozzle. Now things will be more clear from here, and we will see a question of it also. Then it will be even more clear. This is very important part with respect to steam turbine. As far as fluid mechanics concerned with the compressible flow concerned with the fluid mechanics part, we just have to go through it. But for power plant thing, it is very, very important. Okay, now see, pressure tank fitted with a converging nozzle. So let us take some observation. Then apply that in our nozzle. Okay, so we are having a pressure tank now. Let us say we are having this pressure tank now. We are having this pressure tank. Pressure tank is nothing but a large reservoir, you can say, and you can relate it with the conditions of steam exiting from the boiler. But I am trying to generalize the things. So that is why I am trying to generalize the thing. That is why I am using this as a tank. So this is some converging nozzle. You can relate it like this. The exit from the boiler, we had, let's say, one exit to the boiler. Okay, one is exit to the boiler. Let's say the two point is exit to the nozzle or entry to the moving blade. This combined is we call it as steam turbine. Okay, and exit to the moving blade, let's call it 3. So this will be the exit to the complete steam turbine or entry to condenser. Entry to condenser. Yes or no? This is what we read in Rankine cycle. In the first lecture, I have described it in a way. Yes or no? So if I apply, let's say this is my point 2. So if I apply my steady flow energy equation, if I apply my steady flow energy equation, what will happen? Or Bernoulli equation, what will happen? So our flow is isentropic. Our flow is isentropic. Okay. We have assumed that the flow is isentropic. So we can write Bernoulli equation for isentropic flow. We have developed in the previous lecture. So P1 by rho 1 is equal to plus V1 square by 2, and I am neglecting the changes in datum. So I can write equal to gamma upon gamma minus 1, gamma upon gamma minus 1, P2 by rho 2, P2 by rho 2, P2 by rho 2 plus V2 square by 2. P2 by rho 2 plus V2 square by 2. P2 by rho 2 plus V2 square by 2. Is that true or not? Is that true or not? We can write like this. Now, if I assume V1 is very, very less than V2, because nozzle increases the velocity, so we can assume that the entry velocity or the velocity at the exit of the boiler is very, very less as compared to the velocity at the exit of the nozzle. At the exit of the nozzle. Okay. So now, if it is there, we can just neglect it. Okay, and we can write our relation like V2 square by 2 is equal to gamma upon gamma minus 1, P1 rho 1 minus P2 rho 2, P1 V1 minus P2 rho 2. Is that true or not? Is that true or not? Yes or no? Tell me. Is that true or not? Now, someone will say, now here. Don't get confused. Now, if you are, now some people what will do while watching this video, they will open some book as well. Like that, I am just seeing this power plant from Pikinak. I'm seeing the power plant from this book Pikinak. There, they have approached in different way. So there is no different way. Now see. For those, I am just telling you one this. A steady flow energy equation we can write like this: H1 plus V1 square by 2. Okay, and H2 plus V2 square by 2. This is the steady flow energy equation. Yes or no? This is the approach followed by the books in thermodynamics background. It is you can follow Sengel and Boles Anirban if you want to go to. Otherwise, Pikenag is sufficiently good book. Okay, so if you follow a book from the author from thermodynamic approach, you will find this way: a steady flow energy equation. So there you can see we can write it like CPT1. If I neglect this V1 square, so you can write CPT2. Plus V2 square by 2 from steady flow energy equation. Also, we can derive either from Bernoulli equation, either from this Bernoulli equation for isentropic flow, or either from steady flow energy equation we can derive. So from here, we can certainly write V2 is equal to under root 2 times Cp T2 minus T1, Cp T2 minus T1, yes or no? Cp T2 minus T1, yes or no? And you know R is equal to Cp minus Cv. Don't you know that? All of you know that. Cp minus Cv, and Cv is equal to Cp by gamma. Cv is equal to Cp by gamma. Yes or no? We know that gamma is equal to Cp by Cv. Gamma is equal to Cp by Cv. So gamma is equal to Cp by Cv means Cv is equal to Cp by gamma. So we can write Cp in this way. That Cp is equal to R upon gamma minus 1 by gamma, R upon gamma minus 1 by gamma, R upon gamma minus 1 by gamma. So if you place this value of Cp in this equation, in the above equation, which we are trying to derive, which we are trying to derive here. So this will become Cp gamma 2 times gamma gamma minus 1, 2 times gamma gamma minus 1. I am placing the value of Cp. RT2 will be RT2. Sorry, this is Cp T1 minus T2. Na? So it will be T1 minus T2. It will be my mistake, T1 minus T2. Okay, I have sent it from the left hand side. No, so 2 gamma upon gamma minus 1, we can write RT1 minus RT2, RT1 minus RT2, RT1 minus RT2. So V2 will come out to be 2 to the power gamma upon gamma minus 1, 2 to the power gamma upon gamma minus 1, P1 by rho 1 minus P2 by rho 2. From ideal gas equation, we can say P by rho is equal to RT. So here also you can see, you can see we have developed the same relation. Here also we can see you have developed the same relation by using the Bernoulli equation for isentropic flow. So as I am telling you from the very first day that of compressible flow, while we are seeing the flow through nozzle. So if you see this in any book written by the authors of thermodynamic approach, you will find this steady flow energy equation. And if you see the authors of having the fluid approach like R.K. Bansal, Modi and Seth, in those books you will find this approach. So both are the same thing. You can follow whichever way suit you the most. No changes are going to come. Don't do things like that, sir. We are now studying the steam turbine. Now we will study the compressible flow from Pekinat, and now we will change all the concepts. No concept is getting changed. It is same. Either you study with respect to fluid mechanics, either you respect with respect to thermodynamics. So here we are covering a topic which is common in both, and I just have showed you how both approaches leading to the same thing. So is that correct or not? Understood or not? Yes or no? Understood or not? Don't get trapped in these kind of things. Understood or not? Yes or no? Yes or no? Tell me. Is that clear or not? Tell me, we'll move forward then. Is there any doubt till this point? Easy na? Everything is easy na? We are just using the equation we already aware of. Okay, we are already aware of. Okay, so now V2. Now V2 will be. So I think you can play this mathematics. You can play with this mathematics. This is P1 by rho 1. Okay, and this will be 1 minus P2 by rho 2, 1 minus P2 by rho 2, 1 minus P2 by rho 2 into rho 1 by P1 into rho 1 by P1. Yes or no? Into rho 1 by P1, we can write like this. Yes or no? We can write like this. Yes or no? Okay. So our V2 will become. So let me use. We are seeing the isentropic flow. So in isentropic flow, we know that. In isentropic flow, we know that P by rho, that is P1 by rho 1 to the power gamma is equal to P2 by rho 2 to the power gamma. This is the relation we were seen in the last lecture as well. This is nothing but PV is equal to gamma. Very popularly used in reversible adiabatic conditions. PV gamma is equal to C. Yes or no? This is, I just reversed the volume into density. So from here we can replace rho 1 by rho 2. Here we can replace rho 1 by rho 2. We can replace rho 1 by rho 2 in terms of P1 by P2. in terms of P1 by P2 as in 1 by n, as in 1 by, not n, 1 by gamma, as in 1 by gamma. So from here we can write V2 is equal to under root, V2 is equal to under root, V2 is equal to under root 2 times gamma upon gamma minus 1, 2 times gamma upon gamma minus 1, 1 minus P2 by P1, 1 minus P2 by P1, 1 minus P2 by P1 to the power gamma minus 1 by gamma to the power gamma minus 1 by gamma to the power gamma minus 1 by gamma. I have done nothing. I have just placed the value of rho 1, rho 2, the value of rho 1, rho 2 in equation 1. So our equation will be developed like this. Our equation will be developed like this. So I am highlighting it. I am highlighting it because we have developed the velocity at exit of a converging nozzle in terms of pressure ratio. In terms of pressure ratio. Now see here. Look at me. Very, very important. Look at me. So here V2, we can write like this. Now here V2, now see here V2, we can write like this. V2, we can write like this. From V2, we can write like this. 2 times gamma upon gamma minus 1. 2 times gamma upon gamma minus 1. 1 minus n to the power gamma minus 1 by gamma, 1 minus n to the power gamma minus 1 by gamma, where n is pressure ratio, and we can say like this, it is P2 by P1. We can say like this, it is P2 by P1. We can say like this, it is P2 by P1. So if, now see, if we have, okay, sorry, I have left with this P1 rho 1 I left. Here also we have to add this P1 and rho 1 also. Na? In that equation we have to, I left with P1 and rho 1. I am placing this in the equation 1. No. So I have to write this P1 rho 1 as well. Na? P1 rho 1 is also there. Here also P1 rho 1 is also there. Just a typing error. Okay. This P1 rho 1 I have left, so please make the changes, and I am putting rho 1 rho 2 is equal to P1 P2 in this relation. So it is coming out to be 1 minus P2 by P1 to the power gamma minus 1 by gamma. So in terms of pressure ratio, we can write it like this. 1 minus n to the power gamma minus 1 by gamma, 1 minus n to the power gamma minus 1 by gamma. So from these two relations are the same only in the second part I have written it in terms of n. So can we say that? Now listen to me. Can we say that? Now listen to me. If we have, now listen to me very, very carefully. Very, very important thing is coming up for you. If we have pressure ratio. Now see, if we have the pressure ratio n, and if we have the pressure ratio n and the properties at inlet, we can find the exit velocity. We can find the exit velocity of a converging nozzle. Say yes or no. From the above relation, can we say this? can we say this, that if we have the pressure ratio, if we have this pressure ratio, if we have this pressure ratio, if we have this pressure ratio, and we have the inlet properties, we have the inlet properties, we have the inlet properties, we can find the exit velocity of converging nozzle. We can have the exit velocity of converging nozzle. Say yes or no. Say yes or no. Say yes or no. Say yes or no. We can write this same relation in terms of temperature also. Like V2 is equal to under root 2 times gamma upon gamma minus 1, 2 times gamma upon gamma minus 1. So here see, we have replaced 2 times gamma upon gamma minus 1. How we can replace? So 2 upon gamma minus 1 upon gamma. So P1 rho 1 stands for, let's say 2 times gamma upon gamma minus 1. Let's leave it. P1 rho 1 stands for RT1, isn't it? P1 rho 1 stands for RT1, isn't it? P1 rho 1 stands for RT1, and this is equal to 1 minus n upon gamma minus 1 by gamma, 1 upon n gamma minus 1 by gamma. Yes or no? Yes or no? And we have seen already R upon gamma minus 1 is equal to Cp. R upon gamma minus 1 upon gamma is equal to Cp. So R gamma upon gamma minus 1 is equal to Cp. So we can write 2 Cp T1 also. We can write 2 Cp T1 also. Okay. This is just the play of equations, just putting the different values and showing you different relations. They all are the same. They all are the same. They all are the same only. They all are the they all are the same only. Is there an issue? Is there an issue? So if you have inlet temperature, if you have the exit pressure and entry pressure, can you tell me the velocity at the exit of some converging nozzle? Say yes or no. Can you tell me the velocity at the exit nozzle? Yes or no? Yes or no? Yes or no? Yes or no? Tell me. Tell me. So now what we have seen, now let us apply this. Let us apply this first. What we have learned till now. So let's say we have a converging nozzle. Okay, we have a converging nozzle. Okay. I'm not talking about the critical things yet. This is not a critical values. We'll come to the critical values. Okay, now please listen to me. Please listen to me. We have this point 1, section 1. We have this section 1. So we have pressure at this point. We have, let us call it naught. Let us call it naught. So we have this condition. We have this P naught. We have this T naught. We have this P naught. We have this T naught. Or we have this density naught. All are the same, only we know the relation. P naught by rho naught is equal to RT naught. Yes or no? RT naught. So either 2 of given or 3 of given is the same thing only, because you can develop the third one. You can develop the third one. Okay. So the entry condition to U is known. Entry condition to U is known. Now I want you that that's at this exit. Now listen to me very carefully. At this exit, the pressure is, let's say, is known to me. Okay. The pressure is known to me. So from this formula, can you develop the exit velocity? So you can say, sir, yes, I can. But I will say you have to be very cautious here. Because this VE can't be greater than. This exit velocity must not be greater than the velocity of sound. It can only be equal to the velocity of sound. it can be only be equal to the velocity of sound. Yes, Madhusmita, you can. So if it can only become equal to the velocity of sound. If it is going above velocity of sound, this can't happen in converging nozzle. Yes or no? Yes or no? Yes or no? Yes or no? So now, can you understand this fact that with decrease of pressure, the velocity also increases. With decrease of pressure, velocity increases. With decrease of pressure, velocity increases. So there will be some pressure corresponding to this velocity of sound below which pressure cannot be decreased. Below which pressure cannot be decreased. That pressure is called the critical pressure. That pressure is called the critical pressure. So you have to compare this exit velocity. You have to compare this exit velocity, this exit pressure with that critical pressure, and this critical exit pressure must be greater than or equal to, 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 must be greater than or equal to the critical pressure, must be greater than or equal to the critical pressure. If not so, at 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 the critical pressure, sonic velocity will reach and choke will happen. Sonic velocity will reach and choke will happen. Okay. So in this lecture, we have seen the design of converging nozzle. Till what point the converging nozzle, in converging nozzle we can increase the velocity or decrease the pressure. So we will continue from this point in the next lecture. We'll continue from this point in the next lecture. So our next lecture, live lecture, is from 1 o'clock. Please like and subscribe. Please like and subscribe the Gate Academy English channel. Please like and subscribe the Gate Academy English channel to get all the notifications, about the upcoming lectures, the existing Gate syllabus lectures, and everything. The existing Gate syllabus lecture and everything. Okay, everything. So in the next lecture, right from 1 p.m. to 3 p.m., we are going to discuss some of the basics of the nozzles that has left, and we will start with the impulse turbine part 1. So thank you very much. Thank you for seeing this video. Please do come in the next video. Please go and watch the previous video as well. Please subscribe the Gate Academy channel. Please subscribe the Gate Academy English channel. We will be coming back for you with the next lecture. So till then, for now, bye. And thank you very much.